Okay.
Okay, thank you, Cheryl. Hello, everyone. Let's just get started. Welcome to the High Altitude Observatory colloquium. Today, we are very glad to have Dr. Shivaji Chakraborty from Virginia Tech. And next, let me just introduce our speaker today. So Shivaji has been extensively involved in studying the impacts of space weather on the ionosphere through several projects. His research has focused on investigating phenomena such as short wave fade-out, Doppler flash, sudden frequency anomaly, and the sudden phase anomaly using data from ground-based instruments like SuperDARN rheometer and incoherent scattering radar, as well as satellites. And during his doctoral studies, he employed statistical analysis techniques and physical models to gain insights into sudden atmospheric disturbances triggered by solar flares. Specifically, his dissertation concentrated on the effects of flare-driven high-frequency or HF absorption, Doppler flash, and sudden frequency anomaly. And currently, Shivaji is actively engaged in various research projects, including examining the effects of solar eclipses on high-frequency propagation and studying transient effects induced by solar flares on ionospheric electrodynamics. Shivaji is also involved in analyzing electrical surge due to geomagnetic disturbances. He has recently been awarded by the Japanese Society for Promotional Science, or JSPS, postdoctoral fellowship, and the ISEE fellowship, which enable him to conduct further investigations into the impacts of flares on atmospheric electrodynamics. Also, just to add to that, Shivaji was also ASP graduate visitor remotely a few years ago at HAO. So today, Shivaji will talk about characterization of solar flare effects observed by high-frequency radar. So take it away, Shivaji.
Thanks, Don. That's some introduction. Thanks. Okay. Can you see my screen?
Yes. Can I go to full screen?
Yeah.
Okay, looks great.
Okay. So hello, guys. I'm Shivaji from Virginia Tech. I'm a postdoc here, and the talk I'm going to give today, it's related to partially my dissertation or PhD dissertation back in days, and some part of it is like what I'm going to do right now, or whatever I'm doing right now. So it's the characterization of flare effects observed by the high frequency radar. So it's, as you can see, it's predominantly HF radars that is involved in this particular study. So here is the brief outline of my talk. I'm going to talk about the sun and the ionosphere in a very brief way. I'm going to introduce you, if you're not exposed to this particular field of HF and how the radio wave being affected by this ionosphere and its morphology, and also other extraterrestrial events such as solar flares. The objective of this study, the instrument I'm going to use, some of the satellites, some of them are ground-based as rheometer and SuperDARN, etc. And then I'm going to delve into the two different distinct things, which are effect of solar flares manifested in the HF frequencies or trans-ionospheric sky waves. One of them is HF absorption, and another is named as Doppler flash. I'll describe what it is, and some of the other impacts that I'm currently other impacts of solar flare in the MIT system that I'm currently pursuing, and summarize the overall talk. So I think most of you understand what is flare is, but just to give you a brief overview of the flare, it's a sudden intensification of the EM and electromagnetic spectrum, specifically of the sun, specifically in the UV and X-ray region or that band. So here is a snapshot of sun created by the NASA, one of the NASA satellite, that shows a sudden brightening. This is the snapshot that captures the solar flare, and here is the movie that encompasses all of these 8 slides. all of these 8 snapshot. And solar flares are typically often associated with the eruption of the solar energetic protons, which are these grainy looking stuff. Yeah, here is this one, or this particular snapshot where that shows the accelerated energetic particles are coming towards the Earth, and then coronal mass ejection as well. But however, I'm only specifically talking about the flare effects on the Earth ionosphere and communication systems such as HF. Flare can be categorized at five major categories based on flux at this specific wavelength, which is the soft X-ray of the GOES satellite, one of the channel, which is 1 to 8 angstrom. And all of these categorization of the classes of solar flares, they are apart by 1 order of magnitude, you can clearly see. And as you can see, like from the baseline, which is typically A or B, sometimes this X and M class flare that is I'm specifically targeting, they can be 1,000 times greater than the background. So they create a huge impact in the ionosphere and also the HF communication. So the atmosphere of the Earth, specifically, I'm interested in the ionosphere. Earth atmosphere can be subdivided into different regions, specifically based on temperature, and also you can categorize it based on the ionized gases or electron density, such as D, E, and F region. Ionosphere plays a significant role in radio wave propagation because the radio wave, which are used for communication purposes or surveillance purposes, they don't go beyond the peak of the F region. If you get above this F region with the HF communication, they generally don't come back. They actually go and travel to the travel out in the space. So for the perspective of HF communication, this specific frequency range, 3 to 30 megahertz, which is also known as HF, ionosphere plays a very important role to for a long distance communication. It is also known like the ionosphere is highly variable and dependent on different solar activities. So we are going to talk about the flare effects on the ionosphere observed by the HF communication systems such as SuperDARN. So in general, like when solar flare happens, it suddenly enhances the plasma density in the day side D, E, and F region. It's predominantly a day side phenomena. And this overall enhancement in plasma density, termed as SIDs, or sudden ionospheric disturbance, it has different types of other repercussion in different instrument. But here are the major 3 types I'm going to talk about today. First of all, it's known as shortwave fade out. It's the sudden increase of the radio absorption in the high frequency spectrum. And the figure on the right-hand side shows a snapshot or a movie showing how the DRAP2, it's a model by NOAA that shows how an absorption across the day side of the ionosphere following a flare that happened in the Halloween storm, which was one of the biggest flare categorized last 20 or going back to last 20 or 30 years. That shows the kind of depiction of how the shortwave fade out pans out across the day side. And then there is another phenomena associated with that also in the HF that affects the HF frequency. It's called sudden frequency deviation. It's nothing but the change in the Doppler frequency or the Doppler effect enhanced in the HF spectrum. We also call as a Doppler flash. And also there is another part, which is a kind of misnomers to this, just called solar flare effect or SFE. Everything sounds like solar flare effect, but when we talked about solar flare effect, they are sudden transient in the SQ current systems or the electrojets. It's predominantly changing in the day side current systems. That's called solar flare effect. And as you can clearly understand, if you have a change in the current systems, that means there is a change in the magnetic field fluctuation associated with that. And that's called the geomagnetic crochet. So you can categorize the flare effects or SIDs into these 3 broader range spectrum of phenomena. And also there is a phase anomaly, which is associated with the sudden frequency deviation. So, okay, let's talk about the different instrument I used for this study. First instrument is obviously GOES X-ray, because until and unless you record a flare, you can't analyze its effect. So GOES X-ray sensor that measures the incoming flux, which is at the geostationary location, it has two specific channels between 0.1 to 0.8 nanometer and 0.05 to 0.4 nanometer of X-rays. It is given this particular figure. You can see this flare signature. From the baseline, which is around 10 to the power minus 6 watt per meter square, this X-class flare jump, this one was one of the X-class flare that jumped to a couple of order of magnitude, or more than a couple of order of magnitude. So it's almost more than 100 times inflation in the deposited energy on the ionosphere. So another instrument that is called rheometers, that's relative ionospheric opacity meters. It measures the absorption in the D region. That is one aspect of the sudden ionospheric disturbance I just talked about. It's recording the shortwave fade out at the specific frequency band, which is 30 megahertz, which is like almost the end or the edge of the HF frequency. What it does, it's like it directly measures the cosmic radio wave absorption, or it can actually measure the cosmic radio wave cosmic radio noise, and then you can actually find back out some number, how much depletion in that particular measurement due to this after the solar flare. Here is an example on the bottom left side over here that shows a flare goes out, and the black dots are the signature of the shortwave fade out from a rheometer in the Canada, Ottawa. And that shows almost similar looking signature in the solar after the enhancement in the solar flux. Okay, so both of these are, so one of them, like the GOES, is a spacecraft, and rheometer is a ground-based instrument. And I'm going to talk about another ground-based instrument that actually captures the overall state of the ionosphere at SuperDARN. It's Super Dual Auroral Radar Network. The figure shows the overall distribution of SuperDARN radar chains that have been built for an extensive coverage for the auroral zone and the polar cap and the mid-latitude region. And the primary objective of the SuperDARN is to find like the convection mapping in the ionosphere. But it does other things as well. For example, this flare events, and also other things, for example, TIDs and mesosphere studies as well. So what is a SuperDARN do? It's a coherent scatter radar. Unlike incoherent scatter radar, it's coherent scatter, and it operates continuously at the high frequencies. And we are specifically operating at between 8 to 20 megahertz. And by the virtue of refraction and the skywave propagation of through the ionosphere, it can reach over the horizon or beyond your observing horizon. It can reach a greater distance, few thousands of kilometers. And signal can be backscattered from the ionosphere or F-region ionosphere, or irregularities. They are predominantly E cross B plasma, horizontal plasma drift. And these irregularities are typically generated by different processes of instabilities, and they are resulting in Bragg scatter or Bragg's coherent scatter. These specific types of scatter requires the presence of the irregularities over there, and also the propagation condition has to meet E cross B or perpendicularity of the magnetic field lines. So this is one of the primary source or primary target of SuperDARN radar. However, there are other sources as well. For example, the ground reflection from the other side of the from the ionosphere, or it can reflect from the ground. Okay, let me give you a figure that shows how these two different types of ionosphere, these two different types of scatter works. So HF rays can be refracted through the ionosphere in this particular figure, and if there is a plasma irregularities identified by these white vertical lines, they can actually generate these irregularities, and if they're in a motion, you can see this Doppler motion in our HF radar. So they are ionospheric scatter. However, in the daytime, the refraction is significantly higher, and it can refract the ray back to the ground on the other side, which is over the horizon, and it can actually get reflection from the other side of the ground, comes back through the same path and reach the radar. So that's a ground scatter. So these two are the primary source of the target observed by the radar. However, there are other radars as well, other type of target that can observed by the SuperDARN radar as well. And it predominantly SuperDARN radar it's a Doppler radar, so they can actually identify the Doppler shift, frequency shift in this particular region where there is a E cross B drift, and that's the primary data source. So here is a fan plot or scan plot of the radar that shows the velocity obtained from a 2-minute radar scan. This is a capscasing radar, a high latitude radar at Ontario, Canada, and you can see the velocity is color coded by this color bar over here, and the colored scatters, or like the colored location, shows the ionospheric scatter, which are typically high velocity stuff, and this gray location over here that shows the ground scatter, which is because ground are not moving, so that's why you are observing very low velocity ground scatter, whereas the ionospheric scatter typically high velocity. They are typically 100 meters to few kilometers per second as well. And as I told you, it's a Doppler radar. So by the virtue of Doppler shift, the blue color represent the stuff is moving away, or the plasma is moving away, and the red shift means the blue is towards the radar and the red is away from the radar. It's a blue shift and red shift towards the radar or away from the radar. So why do we study this flare effect? So first of all, it's a phenomena that creates a sudden ionospheric disturbance on the traveling radio wave, and it is one of the fastest space weather phenomena observed in the Earth, because it's in the spectrum of EM electromagnetic radiation from the sun, so it reaches the Earth around 8 minutes or so. It's the speed of light. So that's one of the fascinating feature of this phenomena, and also it creates a huge impact on the day side, specifically HF and communication channel that are being used in aviation, emergency management, defense, surveillance, etc., etc. So that's one of the utmost importance for our modern civilization and over the horizon communication channels. And also there is interesting science, is like, for example, this HF absorption I talked about, and I'm going to show it what I'm talking about, and then the frequency anomaly as well. And other things as well that falls under the space science. So first, I'm going to talk about the flare effect in terms of HF absorption. I'm going to show how we have characterized this observation, and how used a physics-based modeling framework to actually estimate the HF absorption observed by one of those instruments. So the flare signature in SuperDARN radar looks something like that. And here is the fan plot that shows the Blackstone radar, that is one of the East Coast radar on the continental US. And here is the field of view of the radar. And as I told you, this is the ground scatter band during the daytime that's going on, because ground scatter has almost relatively zero median or mean velocity. They are very low velocity stuff. And after the flare happened, which is around 22 UT or 2210 UT, we observed something. There was no ground scatter. It looks like the radar stopped working, but it is not. And then after a while, they actually recovered back to the previous shortwave fade out condition, or previous to flare condition. And here is another phenomena that shows a significant jump in the Doppler's velocity, which is not used. We do not used to see that, because the ground, as I told you, like the ground is not moving that fast, and it reaches, you can see it is saturating this color bar, which is around 100 meters per second or so. So this is known as a sudden Doppler flash or sudden frequency deviation. So these two are the primary phenomena that we observed after a flare. So how we characterize the flare? We actually lay down these two data sets. From one of them is solar flux from the GOES data, and we actually have a time series, which is the number of ground scatter echoes we calculate from the radar, each individual beam sounding. So each one of these dots suggests how many number of echoes you get back from the ground scatter. So as you can see, after the flare happened, the number of ground scatter echoes reaches to 0, and it stays for a while, and then it comes back normally gradually to the previous flare effect or pre-SWF condition. And if you time it correctly, you can find out 4 different timings. One is onset, when it started reduction, the number of ground scattered around 5 to 10%. And then when you reaches the blackout phase, where there is almost no communication or HF communication going on, the ionosphere is not suitable for communication at this particular frequency, around this particular frequency, which is like 80% reduction of the number of echoes. And then the onset of recovery, when it started observing again some good number of ground scatter, and then the green line is recovery. And you can see there are 3 phases. You can identify these 4 vertical lines. We call it onset, blackout, and recovery phase. And we can characterize each individual flare event based on these 3 phases. So what we did is like we used all the mid-latitude radar and the high-latitude radar distributed across the northern American sector, and we captured 5 years of events, and we did a distribution. We actually do a statistical analysis based on that. So here is the figure that shows the 3 different types of phases, timing of the 3 different types of phases: onset, blackout, and recovery, as a function of solar zenith angle, frequency, and the peak of the flux, or the peak of the solar flare flux. And what we find, I'll not delve deep down into this particular, but what we find is that like the radio blackout and recovery phase, which is I would say the later phase of the recovery part of the flare, main phase and the recovery part of the flare, that is the mostly controlled by the solar zenith angle and less by the operating frequency and the flare intensity. However, what we find is like these physical parameters, for example, solar zenith angle, frequency, and peak flux, which supposed to be controlling most of this stuff, it has almost no control on the onset timing. It's like we find all of these different radar across different solar zenith angle operating at different frequencies. They are suddenly clobbered their operation simultaneously across the day side. So another fascinating feature what we find for one specific event, that was going back to 2017 September storm event, that shows the solar flare can have different types of impact on our observation. We actually try to categorize the flare based on these 2 terminologies, isolated and compound. How we categorize them is like, if an isolated flare has one sharp peak in the X-ray spectrum, it allows decay uninterrupted, while the compound flare, you can see this part of the flare spectrum during this particular day, it's the 6th of September 2017. It has multiple peaks in the solar flare spectrum before going into like the pre-solar flare condition. So that is what it's like, the multiple short burst of solar signature even before going into the background condition. So that's the compound flare. And what we find when we did this analysis, what we did is like we took one radar, we find out these different individual timings, for example, onset, recovery, and these 3 different phases, and the blackout. We add them up. What we find, they are not linear, or they are not the linear superposition of this individual flare effect for the compound flare. So you can't really add these individual effects observed by the radar. You can't just add them up and you have a total solar flare effect. It's not like that. So it's not so that depicts is like the ionosphere response is non-linear by nature. So here is the small characterization summary. So the major point is like the overall statistically, the flare effect lasts about 60 minutes or so, and it has predominantly driven by the solar zenith angle effect, less of a radar frequency and the peak intensity of the flare. And the onset phase is not none of the physical parameter has any influence on the onset. It is almost immediate across all these radar. However, on another study, what I just talked about, it's like the flare effect. If you divide the flare by its category by individual versus compound, what we find is like the X-class flare has much X-class flare, compound X-class flare has much longer recovery period than an individual flare, and the compound flare is the not it's a not a linear superposition effect of the compound flare is a not a linear superposition of the individual flare effects. Okay, let's talk about the physics-based model we conducted to understand what is an HF absorption, how we estimate that. So, what is the current state of the art? It's the NOAA DRAP model, is the DRAP absorption prediction, which is one of the best state of the art prediction model we have right now. It's an empirical fit function that provides how much an HF absorption should be there given a solar flare effect on it or during an SAP event. However, for Levine et al., that talks about back in 2019, it's a recently published paper that talks about DRAP can underestimate HF absorption during extreme type of events where the X-class flare, where extreme X10 or beyond X5 class events. So the primary limitation of this DRAP model is it only the parameterization of this empirical model is only by soft X-ray irradiance. It does not capture the whole spectrum of the flare irradiance. So we asked this question: can we do a better than DRAP? So we have this physics-based model. I'll not go deep down into this particular model, but what it does in a broader sense, it uses an existing irradiance model, which is UVAC plus, which is old enough. But what we did is like we modified these bins based on the flare impact from the X-ray from the GOES, and it is primarily driven by F10.7. Then we have these background ionospheric models coming from IRI, MCS, and IGRF. And we have these different physical component to that. For example, Chapman layer. We impose the Chapman layer on these irradiance models or UVAC. So that provides us the modified D region, lower E region spectrum, E region electron density. And we have these different wave dispersion relationship along with the collision frequencies. These collision frequencies are, some of them are empirically estimated, some of them are theoretically estimated. And we have these two dispersion relation. And we also have an ionospheric chemistry model, which is called Glukov-Pascoe-Inan model. And we use it to find out what is the enhanced electron density and the absorption coefficient or absorption coefficient height profile. Then we can actually integrate that height profile to find out the total absorption for a specific event. So here is the data model comparison for one of that event. The observation are in gray dots, and this is coming from the Ottawa March 2015 X2.2 class flare. And the combination of different dispersion relationships and different output from different dispersion relation and collision frequency are laid out over here. So this one is DRAP. And you can clearly see there is a significant deviation at 30 megahertz frequency, which is the rheometer observations. And so some of the combination I talked about, given this dispersion relation, wave dispersion relation and collision frequency, some of them are not good. This blue line is not good, but some of them reaches very good at the peak. But as it falls, it looks like there are significant discrepancy. And my understanding is that is due to I'm not actually capturing the recovery or like the recombination rate correctly. Then that might needs to be fixed, or maybe we need some other information in the model as well. So we did a statistical analysis of this model using 21 X-class flare and 37 M-class flare between these 7 years. And what we find is like, on an average, there are 40, this particular model, this collision, dispersion relationship and collision frequency formulation does on an average 40% better than DRAP2. So we are doing quite well, like for a bigger chunk of the event. But one limitation of this particular model, as it's a physics-based model, it takes significantly long time to run. So the throughput is significantly lower than DRAP. So here's the broader summary of this particular study. Is like we do an overall 40% better than DRAP model. So last part of it is I'm going to talk about is the Doppler flash, which is the sudden jump in the frequency spectrum observed by the SuperDARN. So what is a Doppler flash? This is the example I give you a few slides ago, but just a recap. It's a sudden enhancement in the ground scatter, which you shouldn't see in a ground scatter velocity going up around 100 meters per second. Just before the shortwave fade out. So this is the shortwave fade out event where there is no ground scatter coming back at that point of time, but you have a sudden frequency anomaly or sudden jump in the velocity, Doppler velocity, just before that. And Kikuchi et al. Actually proposed one theory that talks about why do we can observe something like that, but they actually did it back in 1980s, and the Kikuchi et al. Suggested there might be two different sources where these things is coming from. It is primarily the Doppler flash is a frequency phenomena or Doppler shift in the frequency spectrum. So what it is going on is actually like there is first part is the change in the D region refractive index due to this electron density shift that actually causes a phase path change in the phase path length. And also there is another cause is like the reflection height of this due to this enhancement in this F region density as well. There can be the rays can be reflected from slightly lower altitude. And that is also this is a physical change in the phase in the ray path. So these two combinations or maybe one of them. And Kikuchi suggested for the flare effect, it is the D region refractive index change that is causing this specifically this Doppler flash because it's a change in the phase path length. So what we did, we actually used a modeling study. Using the FISM2, and we use this FISM2 along with the WACAMX. When we drive the WACAMX with FISM2, it actually can capture the solar flare at a cadence of 1 minute resolution. And then we have a modified ionosphere. And through that modified ionosphere, we actually ray traced using a tool called FARLAP. It's a high frequency ray tracing tool using MATLAB, and also it is available in Fortran code as well. So we used it. We actually did it for first. We did it on May 5th event, which is May 5th, 2015. It's an X-class flare event, and then we conducted a statistical analysis for 10 or 20 events or so. So here is the division of Doppler flash coming from the different stages. One is Doppler velocity due to change in refractive index, which is the top panel for this particular frequency, and then the Doppler velocity due to the lowering of the F region reflection point, which is slightly lower, you can see, and then the final panel shows the Doppler velocity combining these two different sources. And what we find, it's during this particular phase, they matches the observation, which is the red dots over here. They matches the model result quite significantly. And you can see from this point to that point, there is no red dot. That is due to because there are no observation from the SuperDARN radars because of the shortwave fade out event. And they actually matches quite well phase of the Doppler flash. And when we did this specific study for a statistically, what we find is this particular pan that describes in this particular plot. The left-hand side of the plot shows a relative contribution of the Doppler flash coming from the change in the F region reflection height versus the change in the refractive index in red. And on the right-hand side, it shows where the different sources are coming from. Either it is coming from the D region, or either it is coming from the FE region, or it is coming from the F region. Because Kikuchi suggested it is predominantly change in the refractive index. And they also suggested it is predominantly due to this D region phenomena. So we actually laid out two different ways of observing these things, whether this is driven by F region or or change in the refractive index, and where even if it is D region refractive index, where these different refractive index change is predominantly driven. It's D region, E region, or F region. And what we find is like the change in the ray reflection height contributes almost 82%. The change on the refractive index is almost 82%, whereas the change in the ray reflection height is 18%. So it is negligible to refractive index, the change in the F region height, but it is not zero, which is suggested by Kikuchi. And also another point is like the relative contribution to DE and F region among them, the F region is the highest because I'm going to talk about why, but the primary thing is what Kikuchi suggested. It is predominantly D region stuff, D region phenomena. But what we find, it is predominantly F region phenomena, and that even like the D and E region, they are not actually very small. They are significant enough in terms of how you observe this. So it is across the ionosphere, all three different region of ionosphere. So here is the brief finding. The relative contribution of the Doppler flash is predominantly due to the refractive index. However, we do see some changes in the ray reflection height also contribute to this phenomena. It is predominantly F region phenomena, but D and E region also contribute to that. And changes in the F regions is primarily is the driver of this Doppler flash, which is kind of slightly opposite to what Kikuchi suggested, as we find here. So here are the primary questions regarding what we find, and here is the conclusion to that. It's the shortwave fade out. It's a flare-driven phenomena, one part of a sudden ionospheric disturbance, and it is typically stays about an hour or so. It's the recovery phase are mostly controlled by this. The blackout and the recovery phase are mostly controlled by the solar zenith angle. We developed a physics-based modeling framework that performs almost 40% better than the DRAP empirical model. And also, what we find is that the combination of the model using WACAM-X, FISM2, and the FAR lab, we find the Doppler flash can be reproducible in the modeling study. And it's predominantly F region refractive index that is causing this Doppler flash phenomena. Going beyond from this particular study, we have some other impacts on the HF signal as well. So on the left-hand side, it's not an effect of a solar flare, but it's an inherent nature of the ionosphere, which is called ionospheric sluggishness. It is a feature which talks about the initial delay of the ionospheric response following a solar driver or solar flare. As you can see plotted here is like the blue color, blue curve over here is solar flux from the GOES, and then the black dots are the rheometer response. And there is a I do not say significant, but there is a delay of few minutes to few seconds, few tens of seconds to few minutes, and that is called the ionospheric sluggishness. We understand it's an inertial property of the ionosphere that manifests as a lag in the ionospheric response for the solar flare. It's predominantly how the chemistry performs at the D region level that causes this sluggishness to be appear in our observations. And also there is another part to it, part to the solar flare effect. It can manifest as a gradient drift instability. During this particular flare, that shows a top panel by the solar irradiance, and the bottommost panel shows the range time intensity plot from one of the high latitude radar station from the Saskatchewan, and the vertical line shows the peak of the flare. And you can see, like, after the peak of the flare, the radar was operating at the dawn, near the dawn terminator. And as you can see, like this grayscale showing the day-night terminator over here. And we observe some significant enhancement in or appearance of the ionospheric scatter, which is a very high velocity, reaching about few hundred or 300 to 500 meters per second. I'll remind you, this is not exactly a Doppler flash because Doppler flash appears on the ground scatter. This appeared to be an ionospheric scatter, and we wanted to understand what it's primarily driven by. We have some preliminary studies, and we think it is a gradient drift instability caused by the flare. Other impacts of solar flare, we started observing some other HF data, for example, HAMSI. This one particular figure that shows the Doppler phenomena and HF absorption following one X class flare that happened during the beginning of this solar cycle. And you can see this is the Doppler phenomena, and it has actually a wide range of distribution across different longitude and latitude, or maybe solar zenith angle. Collins et al. Published this particular study, and also you can see there is a gradient effect of different longitude that shows a gradient in the HF absorption as well. So we wanted to understand this Doppler phenomena from that particular data set as well, the HAMSI, that is slightly different than how SuperDARN takes an observation in HF spectrum. Few other effect. I talked about another effect called solar flare effect or magnetic crochet or geomagnetic response. They are the recent paper that talks about by Yamauchi et al. That talks about sudden change in the magnetic flux, or sorry, not the magnetic field fluctuation at the different latitude, at the high latitude sector and the mid latitude sector, and also the low latitude sector. That talks about how the magnetic field fluctuation can create different changes in the auroral currents and as well as the SQ current systems. And that is related to magnetic response to it. And also there is a Nature paper recently by Liu et al. That talks about the magnetospheric response, how the morphology or the magnetic convections and also the ionospheric potential can altered due to the extreme X-class flare event. Both of these flare events was studied for this particular flare, almost X10, during 6 September 2017. That was one of the biggest event of the last decade. So, yeah, I'll take a rest here. Any questions, comments? Thank you.
Okay. Thank you, Shibaji. Let's give a round of applause. Okay. Yes. Question time. Anyone, please raise your hand and unmute yourself. Oh, okay. Han Li, please.
Hi, Shibaji. I have a question. So when you did the WACMAC simulation, does this version include the D region or not?
Yes.
Oh, this is the version with the D region.
Yeah, with the D region, because it extended.
Okay.
It started from around, like, if I'm not being wrong, it started around 28 or yeah, I have to check because I don't use data below 50 kilometer, but I think it started way below that, 28 kilometer or so. I have to check with Dr. Kian because she was one of the co-author here in this particular study. Let's see.
Okay, and that's good to know. And also the other thing is when you run this the flare events, do you use a very short time steps? Maybe that's also a question for
Yeah. I actually asked Joe McLerney whether I can actually run it for 1 minute or no, or like 60. Because flare event, what I was looking at, it's sub minute phenomena. The flare event, it's like it is not even stayed there for more than one scan, which is one radar scan, which is like 2 minutes. And actually, I can go like 3-second data. So I was expecting something in the order of tens of seconds, but he mentioned that might not be possible. So we checked for 60-second cadence data for that.
I see. And do you have a comparison with rather than using FISM2, use say EUVAC? Do you have a comparison like that? Comparison simulation?
Comparison with what I'm not completely
with the instead of using FISM2, use like EUVAC or default. The default.
Default run, no, not actually. We like difference because what we did is like we actually did a data model comparison based on the FISM to run and the observation from the radar what we observed, which is in the red. But I guess what you are asking is like whether we have comparison between two model. One is UVAC and FISM. No, we didn't do that.
Okay, thanks.
Okay, thank you, Hanli. Next is Ravina Ken.
Hi, nice talk. How do you segregate the ground scatter from the ionospheric scatter?
Well, so there are few things you can actually. It's not individual. So how we do that? It's like there are few things we looked into our observation. It's a statistical analysis of the observation itself. So first of all, very naively, if I just go and talk about it, it's like the velocity. I just look into the velocity to start with. Typically, ground scatter. If I produce a histogram of ground scatter, they generally the median value or the mean value lies around 0, because that is what the statistical nature of the ground. However, whatever the small perturbation you observe, it is you can observe it in it is coming from the fluctuation of the ionosphere. For the ionospheric scatter, they typically the mean or median it started way above 30 meter per second. Sometime it is low, but most of the time ionospheric scatter reaches around few hundred meter per second to few kilometer per second. So that is how we started. And also where they are located on the field of view plot, that is also goes into this analysis. For the second step is like where it is coming from. We can actually have a good idea about if it is a daytime given a local time where this thing different scatter is generating, because we understand how this propagation is going on given a specific UT time or local time for a specific radar based on the ionospheric condition. So you can actually ballpark some of this information. You can tag them and start gathering information as you grow on these different data sets. That is how you can understand. But it is, I think I'm hand waving some of the stuff which are slightly difficult for me to describe. There is another parameter called elevation angle. You can actually find out what is the elevation. I'm not sure you see my cursor. So there are different rays coming from different elevation. If you have that observation, you can understand where it is coming from. Given that location and elevation angle, velocities, there is another parameter called spectral width. We can gather different statistics and we can identify whether it's ionospheric or ground.
So do they vary in terms of frequency as well?
Yes, they do. They do significantly. For example, if you use higher frequency, the ray can reach farther than a low frequency. Low frequency, because given everything similar, the ionosphere, the elevation angle of the ray, you can imagine like 10 megahertz if 10 megahertz reflect from here, the 11 megahertz can reflect from here. So they can reach the 11 megahertz on a greater distance given 10 megahertz. So obviously the distance and the elevation angle all and along with the frequency, they comes from different location.
Okay, thanks.
Okay, thank you both. I do have a question. Maybe it's too fundamental, but we know during solar flares, actually the irradiance intensity got enhanced at all wavelengths. So, but I think you are mainly referring, or other people also mainly referring to that X-ray band.
Yes.
So I just like how important are the other wavelengths compared to X-ray?
That's a very important question. So if you see, there is a clear difference between how I did this physics-based modeling for HF absorption versus how I used WACMX for the solar Doppler flash, right? So the importance comes with the idea about where this phenomena is happening. So for the HF absorption to be appeared, it's predominantly D and lower E region, not above like the 110 kilometer or so. So for that, if you just tap into the soft X-rays and first few UV bins, then that is good enough. But if you think about, you wanted to if you wanted to understand what is going on at different regions, for example D, E, and F, then FISM 2 that gives a wider spectrum starting at very low frequency, very high frequency, which is like very lower wavelength, around 0.01, I guess, nanometer, and goes around 1900 nanometer or so. You can actually have to, but however, given that whole spectrum, if you go and check some of the recent paper by Phil Chamberlain, the flare irradiance are less than 50 nanometer wavelength are predominantly drives the enhancement in the electron density, even all these different spectrum. Yeah, so I'd say X-rays and UV. FUV, UV, there might not be that important.
So 50 is about the wavelength for X-ray. Sorry,
No, the X-rays are like 0.1, sorry,
0.1,
0.8
I see.
nanometer, less than 1 nanometer are X-rays, I guess. I'm
I
not an
see.
expert, but yeah. But yeah, that is
Okay.
how I understand X-rays. Yeah. So
Yeah, we should
X-rays
be able
and
to.
EUV, extreme UVs, which is like below 30 to like less than 50, let's say 30 to 50. Yeah, that range. X-rays and UVs, they are very important for flare studies.
Okay, I got it. Thank you. And you also mentioned that the other study, the dependence on solar zenith angle. Was that based on a single radar or actually, I mean, multiple beams in one radar or multiple radars?
You mean this one?
Yeah.
There are
We're
multiple
playing
radar.
multiple radar.
There are multiple radar, multiple events.
I see. I see.
So each one of these points, they are each radar event. If you think about it, so one flare can affect multiple radar. So each one of these dots coming from one radar event.
Have you noticed any impacts on the night side where it's not a direct
That's
impact?
a very good question. It's so going back to night side impact. I'm not exactly sure so to have a night side impact, you have to have magnetosphere respond. Otherwise, it's a day side phenomena. And if the magnetosphere respond to that, you might get something on the night side, high latitude night side. But even to excite that's my very naive idea. I'm not completely sure, but I have seen one or two paper that talks about some magnetic field fluctuations on the night side during flare, and they're deep into night side, not like this kind of, I was talking about this thing, right, which is like grazing angle or relatively around the dawn dust terminator. Not like that. It's somewhere here. They observed something back in the paper was by, I forgot the name, first name, but yeah, it was related to magnetometer studies. But yeah, that's my understanding. It's not like the flare can directly affect the night side, but what it can do is like it can excite the magnetosphere such a way that it generates some instability or maybe some mechanism it can excite the night side. Maybe that one of the cause. But I have seen only one or two paper that talks about, and that is also 1980s, something like that. Yeah.
Yeah, I believe there should be some new fields that we can explore. I think one possibility is that the conductance got changed so that the convection pattern also got overall changed. But yeah, we can probably continue the discussion later on. Just to ask again, anyone else having further question for Shibaji before we close today? Okay, if not, let's just thank the speaker again, and also thank you all for coming. Thank you, Shibaji.
Thanks, Dom. Thanks for inviting me.
Yeah. Okay, have a great day, everyone.
Bye all.
Yeah, see you.